Hi guys, welcome to Recitation 3. So we'll be posting the slides and the notebook after the recitation, so you won't be having it right now. So just you can follow what we're saying and probably look at the slides later. So how many of you have gotten started with homework 1? Okay, that's a good number. All right, so if you attended the last recitation, you'll know that we were discussing about how to build your training loop, how to evaluate, and how to load your data, how to represent it, and how to add layers, etc. Even if you do all of this, for the second part of the homework, you will also have to use some optimization tricks. You can't just use linear layers and get away. You can probably reach the B cutoff, but for A, you should do some kinds of optimization. Even otherwise, when you build neural networks, there are some optimizations that you can do in order to boost your performance. And today, we'll be going over a few of them so that it will be helpful for your homework 1 part 2, and also later probably for other homeworks. So first, we'll go over some optimization techniques, and then we will explain how it's generally used in practice, and then we'll go over a notebook where we have all of these coded in PyTorch so that you can directly transfer them to your homework with minimum modifications. So Bhiksha covered gradient descent in class, which is basically trying to find you're moving in the direction of in the opposite direction of the gradient in order to find the minima. And you basically traverse in a particular step size. But then what is the problem with gradient descent? You're trying to perform a weight update only after you've done a complete pass of the data set. So suppose you have 100 training instances, you're doing a weight update only after you see all the 100 training instances. If you remember how Bhiksha was going about gradient descent, it's almost like you have some kind of a curvy surface and you're trying to fit a cloth over that. And so when you try to make an update after 100 training instances, you're introducing an average kind of an update where you're not giving enough variance to different training instances. So what we want to do is probably take these training instances in smaller sizes and make sure that we have a higher variance than averaging out everything, because that way you would sort of consider all the training instances and you're not considering how much variation small batches of it give. There is another side to the extreme, which is stochastic gradient descent, where updates are performed after every training instance, but this will give you a very high variation. So what we do is we try to find a middle ground, which is mini batch gradient descent. In mini batch gradient descent, you perform update for every mini batch of data, which is you split data into small batches, and then you perform weight updates. And why is mini batch gradient descent useful? Because it allows us to use the whole data set. Gradient descent uses the whole data set for one update, which makes the process very slow and intractable for large data sets. Once you start homework 1 part 2, you will realize that you can't put all of your data set in the GPU memory. You have to take small batches of it. And if you do the other way around, which is stochastic gradient descent, which is updating it for each point, you will find that there is a very high variance. So we find a middle ground, which is chunking out small parts of the data. This is the traditional convention that we follow, where you have f, which is a function, which is our model, and then say we have theta as the parameters. Then we find y hat, which is the output that we are giving from our model. So we know that the model is a function of the input and the parameters. And we have some kind of a loss function, which we try to minimize on the data set, which is, again, a function of the output that we produce from the model and the gold standard output. And if eta is the learning rate, then what we do in a mini batch gradient descent is that we average out for a small batch, where m is the number of instances that you consider in this particular mini batch. And the rest of the process is similar, just that you're taking small steps in the opposite direction of the gradient. You're not considering the whole data, or you're not performing updates for each data point. So what are the good things about mini batch gradient descent? The good things are the fact that it reduces the variance of updates as compared to stochastic gradient descent, and increases the variance as compared to gradient descent. So you're sort of finding a middle ground. And then matrix multiplication is now faster as compared to gradient descent, because you have smaller matrices. And but then now we have to decide what the sizes of our mini batch will be. So this is very dependent on the kind of problem you're trying to solve, the number of features you're using. For instance, in your homework 1 part 2, you have 40 features for each given frame. There can be different language models where you probably have vectors of size 300 or 400, where each of them is word vector representation. So depending on what the size of your features is, you have to decide the batch size, because you must basically make sure that whatever batch size you're giving must fit into your GPU memory. I think most of you will probably be using p2.xlarge now, which has like 11 GB of memory. So I think most of you know that, I mean, when you start homework 1 part 2, you should know that there is this command called NVIDIA SMI, where you can understand how much of the GPU memory is being used and how much a compute is being used. So what you have to do while training is make sure that you're making the maximum usage of your GPU and make sure that you're not running out of memory as well. So generally what we try to do is try giving it numbers between 32 to 256, your batch sizes, so that you know, when you're increasing these sizes, if you run out of memory, then you reduce the size. Just do a trial and error thing and make sure you use the maximum compute as well as memory. And if you have very small sizes, again, you have the problem of running into high variance, and also the fact that your training is slow, because now you're taking smaller chunks of data, you must perform more cycles. And if you make it too big, then you will find it hard to escape from the local minima, because you're going to miss out some small bumps that you may have, and you're just jumping across all of these. And if you remember the process of gradient descent, any kind of gradient descent when you do, we know that the loss is a function of many weights and biases. We are supposed to be updating all these weights and biases, and all of them are have different curvatures and different eccentricities. But what we're doing is we're taking a step in one particular direction, and what might happen is probably you're going too fast in one of these dimensions and you're going too slow in the other. So assume that we have, say, 2 dimensions that we must update, or 2 weights that we must update, and one of them is extremely flat and the other is extremely steep. And suppose you have a very large step size, then you will make sure that you're going in the, I mean, if you have a large step size, then probably it's helpful for the steep dimension or the steep weight. If you have a very flat one, then probably you're going too slow on that. So since we have one step size, it might not be the optimal step size for all dimensions. And this can result in convergence of one dimension while causing a divergence in the other. Bisha will cover all of this in more detail, but we're just giving you an overview so that you can get started. And what do you do for this when you have different curvature in all directions? So one very intuitive thing that you can do is try to normalize this and make sure that the curvature in all directions is sort of normalized and they have similar curvature. But this is a very exhausting process to do. It takes a lot of time, and then after doing these normalization, you can only use second order methods, which will consume even more time. So generally, people don't resort to doing these normalizations. What is a more faster thing to do is to treat each of these dimensions separately and to update them separately. But what happens in this is the fact that you're not considering the dependencies between different dimensions. So basically, probably you're going in one direction for one weight and just the opposite direction with respect to the other weight. So you're basically canceling out your actions. So we also need to make sure that we consider dependencies in each of these dimensions. At the same time, we don't go too forward in one dimension. We sort of average out everything. So there are some algorithms like the rprop and quickprop, which Biksha will be covering if he has not yet covered it, where the dependencies between these dimensions are ignored. But again, capturing dependencies also might be pretty helpful for a lot of problems. So what we do is try to use momentum methods, where we maintain a running average of all the previous steps. And what happens is when we are making a weight update, instead of just using the gradients that we have for this time step, we average out gradients from the previous time steps and use that value in order to update our weights. So when we do this, what happens is that in the directions where convergence is very smooth, the average will have a large value, and where in directions where the estimates are swinging between positive and negatives, the average will somehow cancel out them. So you're basically getting out an average where you don't want it to be too much or too less. So what we do is, like I told you, we are going to update the running average than the current gradient. That's where momentum methods are used. So if you see this diagram where we are using just gradient descent, I mean, it's flipping a lot between positive and negatives, but once we have a running average, we make sure that we go proportionally in each of these directions. So momentum reduces updates for dimensions whose gradients change directions very often, and increases updates for dimensions whose gradients point in the same direction. So momentum methods have also been optimized over the past few years, where we have small things that can be done to the math and made sure that we handle more cases. RMS prop is one example where you use a variance-based update. Instead of using the average, you basically consider the variance and then use the mean square derivative of this variance. Basically, you're using a second-order method instead of using a first-order method. And there are other things like Adam, where you consider both the second order and the first order, which is both the variance and the momentum in terms of the average. And you can also go back and look at different variants like Adagrad, Adadelta, and Adamax, which are just small variations of these methods. Another important thing that you can do in your assignments is to do parameter initialization properly. Suppose we started off with giving 0 initial weights to all our weight vectors, then what happens is the derivative with respect to the loss function is the same for all w. So we'll have the same weight values in subsequent iterations, which is not what we need, because gradient descent is a stochastic optimization technique, and it is better off if we have random initializations, or basically different kinds of weights, because we're searching through a huge space, and we don't want everything to be same. We're trying to sort of fit our model on the data. And what if we had all equal initial weights? Then it's very harmful for something like a stochastic optimization technique like gradient descent, where we have to search through a huge search space. And in this case, what will happen is that all neurons will follow the same gradient and will end up doing the same thing. But that is not what we want to do in neural networks. We want to make sure that each neuron is looking at a different part of the data and capturing differential information, which is useful for the task that we're performing. We can do different kinds of initialization. One of them, like I said, is do a random initialization. There are other polished methods like Xavier initialization or pre-training, where you pre-train your network on a different data set and then transfer it on a new data set. You will probably not be using pre-training because we want you to work on just one data set for now. You can use random and Xavier, and we'll go over it in the coding part of this recitation. And another important thing that you can do is to anneal the learning rate. It is useful to reduce the learning rate over time to make sure that you cover all the bumps that are there in your function. Higher learning rates can cause the parameter vector to bounce around chaotically, unable to settle down into deeper but narrower parts of the loss function. You can do different kinds of learning rate analysis, like for the first one is a step decay, where you reduce the learning rate by some factor after a given number of epochs. Say you have something like after every 5 epochs, multiply my learning rate by probably 10 power minus 1 or something like that. That is step decay. A plateau decay is where you watch the validation error while training with a fixed learning rate and reduce the learning rate when the validation performance stops improving. So basically, every time you're running a loop, you also know the results on your validation data set. Once you know that your model is no more performing better, I mean your performance is not increasing with every epoch by a given factor, then what you do is you reduce the learning rate and tell your model that, okay, you can learn more slowly and catch all the small bumps that are there in the function. And you can also use exponential decay, where you basically use the exponential function in terms of the time step, where the hyperparameters are t. K is the hyperparameter, which you can set, and then t is the iteration number. So basically, as the iteration increases, you exponentially decay your learning rate. Another very important optimization method is to do a dropout. So what dropout does is it makes neurons forget their values randomly. So dropout at you give a probability of p with which different units can forget their weights. So in this way, you're making sure that you're not basically mugging up the data that you have. You're generalizing it better by randomly allowing neurons to forget some values and re-update them. So what happens in dropout is the fact that the network is forced to learn a distributed representation, which sort of improves the generalization. And we generally set dropout probabilities to 0.1 or 0.5, I mean from 0.1 to 0.5, so that you do not completely forget these values, but you're somewhere catching the middle ground and saying with a probability of half, allow some neurons to forget their values so that they can be re-updated in the next few training instances. We will also go through how to implement dropout in PyTorch. Can we get done? Another important thing that you can do is batch normalization. Batch normalization will be covered in detail in probably the next or the next to next lecture. But we'll just go through a very high overview, which is we assume that every mini batch, when we are performing a training, is statistically similar to every other batch. But then in real world data, there is a lot of difference between different batches. I mean, the values that we get or the feature representations can be really different. What happens in batch normalization is that you try to somehow bring these values together, or you basically try to do a normalization of training instances so that the covariance shift is reduced. The covariance shift is basically how these mini batches are statistically very different and varied across different batches of data. So what we basically do in batch normalization is we move all the batches to have a mean of 0 and unit standard deviation. And once we have moved it, this is as good as moving all the data to the origin, and then we move it to a required destination. This is pretty much like doing a normalization. This process eliminates the covariate shift between batches and then makes sure that the training is faster because you do not have two varied mini batches. And this is done after the affine combination of inputs. So when in a neural network, when you assume, so what you do is you first have inputs, then you perform an affine combination, and then you apply activation. So batch norm is done before the activation, which is you do the batch, you have the batch normalization layer at the Z part of your neural network. So it aggregates the statistics over a mini batch and normalizes the batch by them. That is a very broad overview of what batch normalization does. Probably you will have, say, half a lecture cover batch normalization where you'll understand the math behind it and how to go about it. So other general things that people do are to use a scheduler. We will also go through the scheduler part where you sort of check the validation accuracy or any metric on the validation data set and try to reduce the learning rate when there is no improvement in this particular metric. And generally, when you're running different epochs, you have to make sure that you shuffle the data set. If you're using the data set in one particular order, then your model is basically learning the same thing every epoch. So no matter, say you run it for 50 epochs or 100 epochs, you're basically going in the same direction and the model will never be able to generalize. So shuffling is very important, and to make sure that your data order is not remembered. And there are also some things like weight decay and L2 regularization, which is similar to what we do in machine learning. Like we introduce a slack factor where apart from the loss function, we also add this, like we do in ridge regression or something like that in linear regression problems. And you can also do early stopping so that you don't overfit on the training data. So once, when you start training, you realize that at a point of time, your training accuracy is increasing, but your validation remains the same. That is when you have to realize that you're overfitting the model, which means the performance will be very bad on the test or the validation data set because you're trying to basically fit your model to training data. So that is when you have to stop, when your validation performance stagnates and your training is constantly increasing. You basically do an early stopping to make sure that you do not have an overfit model. So Hannah will go over the code, and yeah, you should be able to understand how to implement all of these in PyTorch. Oh yeah, I can go to him. You can probably start. Oh sure. Yeah. Yes. I don't get your question exactly. Mm-hmm.
where you take like a different trade-off. Is it something similar to that we are doing here, or is it like a different theory where you have this container?
No, I think it's not all that complex. We might not have to go to the exploit versus explore paradigm and all of that. It's basically allowing your neurons to refresh and make them learn things again because they do not memorize something. So the whole point of doing all this is to make sure that your network is not memorizing the data. It's able to generalize better, and it's able to classify instances that are a little off from your training and not just memorize what's happening in your training. Oh, because what? Oh, so his question was, how does the model remember the order of the data if you don't shuffle it? So basically, assume that you have some particular features, and say your curve looks something like really high on the top and then low later on in terms of the feature representation, right? There is, okay, I can't use the blackboard, right? So basically, say we have a curve like that, okay? So if you don't shuffle the data set, what is happening is every time you're just going through the same curve. But when you shuffle it, you get a different graph altogether, right? Pardon? So it's dimensions versus time. So basically, with different time steps, how your the curvature of your function changes. So that curvature will totally change. I mean, when you, so you have a time, and then you say we just have one dimension. So you plot these points with respect to time. So the curve, this is the x-axis, and this is your dimension. So basically, you're getting the same kind of a curve if you don't shuffle the data set.
So I'll be going over the notebook. Can everyone at the back see it? Is it big enough? Or should I zoom in? Is it okay? Okay. So, thank you. So to answer the question about the shuffling, so in this notebook, we'll be using a data set which is the fashion MNIST data set. So it's basically images of clothing that we're trying to classify. And this is just the initial part, is just the basic data loading using the API and setting the classes. We have 28 cross 28 images, and there are 10 classes of clothes like shirts, trousers, etc. You can see here. So if you think about your data set, suppose the person generating the data set had all the shirts, then all the trousers, then all the dresses. And if you train your model on that, your model will start to remember that they came in that order, and it will assume that your test set will also come in a similar order, but that's not true. You don't know anything about your test set. So you want to be able to make sure that you remove all the possible dependencies in your training data set, and shuffling is one of the methods we do that by. Shuffling basically eliminates any kind of order that may have been in the training data set. So these are just a couple of pictures to help you visualize what the data set looks like. And we're starting off with a very, very simple MLP with just 3 linear layers. And it has just a transformation from the 28 cross 28 into 64 features, etc. And then finally, we're just classifying into the 10 classes. This should be familiar to you from how you've seen models being built in the previous recitation. And now we'll look at the different types of optimizers that Aishwarya mentioned in the first part. We'll look at how we can implement them in PyTorch, and this should also give you some intuition for the things you're implementing in part 1 of homework 1, because you're basically rewriting these in NumPy. So the notebook here, I'm skipping over some parts because there's a lot of text for you to be able to read and understand when you're looking at it on your own time. But for now, we'll be going on and I'll be talking you through it. So this is just the basic data loaders, and then we're writing like a training class lower down. But here we have a class for the trainer. In the previous recitation, you may have seen a simple function and a for loop. That's perfectly fine. We're just showing you the different methods that you can use, and you can use whichever one comes more naturally to you. Now, in this first part, we are writing the we're looking at learning rate scheduling. Now, if you remember that Aishwarya mentioned that when you train, initially you want to train over larger, you want to train faster, you want to jump greater because you don't want to be caught up in local minima. But once you come into, suppose, a section of your curve, you don't want to keep jumping around. You want to be able to converge to that minimum. So you would want to decrease your learning rate. You don't want to start with a very low learning rate in the beginning because then you'll just take very, very long to train and reach that minimum, and you might just get stuck in a local one. So a way that you can do this in PyTorch is to use the scheduler, which you can see over here. You can see the scheduler is being used over here where we step with the scheduler. Sorry. And what basically the scheduler can take a parameter, which is you can either choose to decay the learning rate or you can give it a list. And then there are all the methods that Aishwarya mentioned where you have the step, you have the plateau, and you have the third one was exponential, which is the parameter. When you're training, you need to also remember to always set your optimizer. You have to zero grad your optimizer. What this means is you're basically setting all of your weights and biases matrices to zeros. This corresponds to the function in your homework 1, part 1, which is 0 grad weight and 0 grad biases or something like that, something of that format. Because when you're training and when you do backwards accumulates the gradients. But the gradients of one batch are not necessarily relevant to the gradients of another batch, so you need to zero grad them out in your for loop. And then when you have to call the optimizer step function after you call backward on your loss. If you think of it intuitively, the last thing you did in your network is you calculated the loss, as in the difference between your prediction and your actual label. And then once you've got the gradient of that loss, you can now optimize based on that, as in you step backwards. That's how you should think about it. Now we'll look at some initializations. So for this part, we're just looking at a normal initialization between 0 and 1. And we'll compare the effects of using SGD, Atom, and RMS prop in PyTorch. So we're using the same model, except for the only difference is the optimizer. They've all been initialized using the random normal initialization. When you see the results, you'll notice that the convergence for Atom and RMS prop is quite similar, but for SGD, it takes much longer. So if we look at the plots, we can see that the training loss for SGD falls to 0.02 after 7 epochs, whereas for RMS prop and Atom, it falls a lot lower in the same amount of time. And you can also see that your accuracy is higher with Atom and RMS prop. There is difference between the two of them as well, because of the different reasons that Aishwarya mentioned in the first part, where Atom and RMS prop have optimizations that SGD does not. And also, like, generating these plots is a good way for you to also check your code when you're coding part 2, because there are a lot of times when you might not be getting results, and you don't know if it's because you're doing something wrong when you're actually generating the labels, if your model's not training. So this can be something very helpful. So you can use this code as well. For parameter initialization, we saw the random initialization, which is repeated here. Another way is you can define a custom initialization any way that you want. Sorry, there's a question? Yes. So it depends. So the question was, why do we need to schedule learning rate separately with Atom? Because Atom already decays as part of the Atom algorithm. So Atom decays as part of the algorithm. You might want to add a plateau condition, where if you reach a plateau, you want to continue decaying, and you might not be using Atom. So this is not a one-size-fits-all recommendation for what to use. Adam is normally the go-to, but you can find research instances and data sets where you'll find that different methods, such as even SGD might, with tweaks you make, be a better optimizer. So you can get more control by that, and then you can use the scheduler. Does that make sense? So this is what Aishwarya was mentioning about using pre-training for your weights. This, again, is not relevant for homework 1, part 2, but you might want to use it later on in the course, where you would just have a weight matrix already, and then you would copy those weights over. You could define this yourself. And then if we wanted to do Xavier initialization, we could do it this way. So this is basically translating those formulas into code for you. And here you can see some of the results from using Xavier and normal initializations. One of the things that I came across is that there's not necessarily a better initialization method empirically, research-wise, but one of the good things with initialization is it gives you a very good starting point for comparison. So if someone were to use your model or you were to retrain your model, you don't want the initialization of your parameters to be causing differences. You want the differences to be the things that you made. So limiting it to like normal or Xavier gives you a bit of consistency across your trials. So this is the plot for Xavier and normal. They're fairly similar, but you can see that one is steeper, and then they reach different points. And again, this is for one data set. This is for fashion MNIST. The effects may or may not be different for different data sets and different models as well. So this is also using the pre-trained weights. This is similar to the copy method. And Aishwarya mentioned momentum as being able to accelerate the gradient in a direction. You can also use momentum in PyTorch within the batch norm function. So we'll see that lower down when we talk about batch norm, because momentum is already sort of taken into consideration in optimizers like Adam, but batch norm itself can benefit from using momentum. And the value that you use for it is something that you can play with, or you can make it a hyperparameter. So as Aishwarya mentioned, batch norm is to try to eliminate the internal covariate shift. This comes back to what we were talking about, where we want to try and make our model general. We don't want it to be too specific to our training data set. So if we were thinking in the context of this clothing example, suppose for some reason that all of our training data set had clothes that were red. When it comes to, suppose we were testing that model on normal clothes pictures, then those clothes might be red or blue or green or whatever. But our model has already learned how to pick out the outline of a shirt from a dress or from a shoe. The color, it's the same distribution because they're all clothes, but the distribution is now shifted in our test data set. So that's an internal covariate shift. If you were to think of both of them just as bell curves, the red one would be here, and if you had all black clothes, it might be just the same curve shifted over. So what batch norm does is it allows you to generalize away from that kind of a shift in distributions. That's what internal covariate shift is. So batch norm this is the way to implement it. And lower down, we'll show you how to just call it in PyTorch. There aren't normally many things that you need to change apart from the parameters directly visible to you, so you shouldn't need to edit the class. Overfitting, as Aishwarya mentioned, we're trying to generalize, we're trying not to overfit. So shuffling we already did. Dropout is the other technique that we mentioned. And as Aishwarya said, it's to try and make the model just force it to stop memorizing and change its weights over an iteration. Just remember that you do not do dropout when you're testing. Dropout is only for training, because when you're testing, you don't want to lose any of your weights. Your model is there and ready, and you're not dropping anything out. When you train in PyTorch, you set your model.train. And then when you are in eval, you do model.eval, and that automatically signals to dropout to not act as dropout in the evaluation of your model, of your data set. Another thing is weight decay is a regularization method. And weight decay is, for one thing, it helps you prevent the exploding gradient problem, because your gradients can get so big that you just reach nans. The other thing is it helps you regularize in general. And you can see here that you can add it as a parameter. It will just be a multiplier on what you multiply what you're adding your weight with. And it's another technique you have in your toolbox. The other thing is you'll see all the different results on this data set with using the different techniques we're mentioning. Gradient clipping is also to prevent the exploding gradient problem. That what happens is your numbers just get too big as you're training and you just keep on adding. So clipping helps you keep those within a certain limit. Annealing the learning rate is basically decaying the learning rate. So like we said, you want to be able to control how and when your learning rate decays. The scheduler gives you more control, where you can say, okay, after this many epochs, do this. Whereas annealing is just a constant factor. So are there any questions on any of this? Yeah. Yeah.
Because the distribution or the input of each layer changes without the parameters in the previous layer.
Yes.
So why is it that we apply batch normalization after Wx plus b in a particular equivalent?
So I'll just repeat the question. So the question is that batch norm the function is to reduce an internal covariate shift. So why are we adding it after Wx plus b in our neural network? So by that you mean after the transformation, but before the activation?
Yes.
Okay.
Not right after that.
So you can do both ways. So in our code here, actually, we are applying it after the activation. So if you see here, we've defined the model in this way. And the way that we call it is we do the first layer, we apply the ReLU activation, and then we have batch norm on which we call dropout. So either way, because it's the output of the previous layer, is you have your transformation, you have your activation, and then that's what would be coming into your layer. You can apply batch norm there.
It's just traditionally applied after the affine combination, because once you have the activation, you're losing out information. You're sort of introducing nonlinearity there, so it's just people have figured out that it's better if you apply after the affine combination than after the activation.
Okay, so Ashwarya is saying that people have noticed that it's better to apply it after the affine combination because you might lose information after the activation. Yeah?
And also there are some learnable parameters in batch norm. That is why we don't apply it just on the data set. We do it in the layers of
Right.
the
Right. And there are learnable parameters in batch norm itself, which is why we don't apply it directly on the data set, but we put it into the neural network. Yeah. Are there other questions? Yes.
So why have you only considered the covariate shift? Why aren't we considering the shift in the means of the distribution?
So covariance shift is a measure of your distance from the mean, right?
Per distribution.
Right. So
Then you have
per
different
batch.
distributions.
Yeah.
Then the mean also is a measure of how different those distributions are.
Right, but the whole point of batching, so remember Ashwarya talked about how you could have SGD, which is just per example. Sorry, so the question was, why are we only worried about internal covariate shift and why not the means across the different batches? So when you have, the point of having batches and training on batches is to get the best of both worlds of training on examples and training on the entire data set. Training on the entire data set would give you something, you can just hit a local minimum very quickly. You want to some extent learn specifics of a batch, right? So, but not to the extent where you're learning everything about every single example. Do you understand? Does that make sense? So like you don't want to generalize too much. You want to learn some of the specifics, which is why you're trying to overall reduce the spread of the data, but having the different means is okay. And having done shuffling beforehand and the different methods, you shouldn't be having a batch which is too different from the other batches. If that's not clear, we can talk about it more after. Yeah? Yes.
How does the neural network learn about the input order?
Sorry?
How does the neural network learn about the input order?
So how does the neural network learn about the input order? It's not that it's intentionally learning about the input order, but it might become dependent on the input order if the order helps it predict better. So if I were to tell you, I have a box of objects, and I'm going to give them to you one by one, and I want you to remember the objects. So like, tell me later what they are. If I gave you all the car toys before all the dolls and then all of the, I don't know, some other toy, then you would be able to remember the order as opposed to, oh, a car has 4 wheels and a bike has 2 wheels, if that makes sense. Does that make sense? So you would take that as a shortcut to learning. So a neural network is literally just a model of how a person's brain would learn something, right? So if you can find a quicker heuristic to learn something, because when you're learning, all you have is your training set. So if you can find a quicker heuristic, you'll use that. Does that make sense?
But then in that heuristic, the loss function has to decrease after we have seen cars, right? Like, we internally are not really using loss functions. When we are memorizing the order, the loss function should change. But if it's
Right.
saying loss function, how does a loss function suddenly decrease after you have seen a cat for the cars, for example?
So the loss function is comparing between the label and the true value, right? So when, sorry, can you repeat the question? I don't quite understand.
The loss function is not dependent on the previous output, right?
No.
Then how is it able to realize that, oh, we have seen all the cats, now it's our turn to see the cars? That is, if we have seen a car, the cat should have passed by now. If it's not remembering the previous input.
Yeah. Can we pull one of these up? There's chalk here.
So we're talking about something like this, okay, through time, and say this is the curve you have with respect to one dimension, okay? What you're trying to do is you're trying to fit your model to this curve, right? So suppose I shuffled all of this, then I would get a different curve, right? So your model will generalize better. But assume you're doing just this every time, which is giving it in the same order, you will just basically try to fit the model on this curve.
So do
You get
we randomize after every epoch, or we just
After every epoch, yes. Yes. Does it make more sense now? It's time. It's basically, say this is the first instance, second instance, third instance, fourth instance. Time steps, basically. Or say the number of instances if time does not make sense to you. Which, this is just one particular feature, and this is the number of the instance. The first, second, third, and so on. Yeah, your model is trying to use some particular metric in order to fit over your training data, right? This value for it can be anything, like some function of the feature that I have, right? We could probably discuss it in detail later, maybe.
I mean, we have time. I don't understand the question.
Or they're basically saying how is the memorizing happening. Okay, we can probably add more slides on your recitation as well, which gives you a better picture of this. Because probably if we show you the curves and explain, probably remember the lecture curves, then you'll get a better picture.
But just for us to be able to put that in, can someone explain which part is not clear about the memorization? So either of the people who were asking. Like if if you have a graph like that one, and that's your entire graph, that's what you're learning, then you can just memorize that, right? But so suppose the first data point was what we were mentioning as cars, and the next one is cats. So if you know that you always have cars and cats, then you'll be able to memorize that. But that won't abstract to your testing. Sure.
I think it's kind of weird because at test time we're not feeding in multiple instances, we're just like testing one thing. So it's not like, let's say remember, it seems like at test time we would remember like, oh, I just saw a car, now it's like a cat.
No. Oh, sorry. Okay, so he's saying that you're thinking that after I've seen a car, I'm going to see a cat. That's what the dependency is coming in as. Is that what you're asking? Okay, so you're not learning that.
You're basically training your weights in that.
Yeah, so your weights basically represent this curve, right? So it's not specifically the order that's learned, but the curve that's learned assumes that, right? So the curve assumes that you start with, sorry, yeah, okay, so it's not start with, like, I don't know how to explain it in terms of once if you saw the same thing over and over and then you saw a different thing, right? And when you're testing, it's expecting not to see the same thing over and over.
I don't know, thinking of it in terms of order doesn't make sense.
Yeah.
It's just that the weights are trained in such a way that it fits
Yeah.
that curve and you basically
Okay.
change that curve.
Yes.
So, at least from what I had understood was that in mini-batch gradient descent, we want the gradient of the mini-batch to as accurately represent the whole data set
Yeah.
as you want.
Mm-hmm.
So when you have samples that come from a biased part of the data set, which is only a few parts of the data set, the gradient will be with respect to only the classes that are present in that mini-batch.
Yes, that's true.
So I don't see any time modeling that the network is doing. I cannot really understand as to how it is learning sequences over time. But if, say, the data is in a particular order, then at least this fact makes sense to me that the gradients will be dependent only on the classes present in that mini-batch.
Yes, that's true.
It doesn't make sense to me how the network is memoryless. How does it remember what it saw on the last time?
I mean, this is not what the model learns. It's just to give you a more intuitive explanation of the curve in general. So it's not time exactly. It is memoryless. You're right. I don't know. I'm just not getting the right words. Probably we will put
can
more
put a
slides
post up.
and you can understand it better. Also, Diksha will be covering it in the lectures.
Correct me if I'm wrong, it's more like you have a lot of features, and then as you know, the neural networks are like less on bias, that is, they don't shift. So if your entire data is in an order where one of the feature has high bias here, high bias down here, and what happens is in the end when you have those important features, it won't shift, the boundaries won't shift. So that is why you shuffle it to make sure it learns it. So when it refers to what you're saying here is more about the order, right? It's not the time order.
Yeah, it's not the time order basically. There is no notion of time basically. It's just how you give your instances, and I just synonymize that to time. If that doesn't make sense, yeah, that what he said also makes a lot of sense, that you're trying to make sure that you don't give it in the same order.
But we'll definitely clarify this and either put it on these slides or on Piazza as a post. Any other questions? So one of the common questions that came up regarding homework 1 part 1 was when you're using the log sum exp trick for softmax cross entropy, there's a term A, which is basically your addition, and then you're abstracting that in your log part, right? Do you recall that? So one of the questions was, what is A? How do I know what A is? Does anyone have an idea on what A should be? Yeah, so the answer is you take the maximum among your maximum out of your matrix. Do you want to explain why? Sorry?
So that it basically makes sure that it normalizes it in
Yeah, so it's a way of normalization because the problem is that you're getting nans. So the most likely to give you a nan is the biggest, is the maximum in your data set. So you normalize by subtracting that from all of your data points. And then the log and the exponential helps you basically avoid the nans. Does that make sense? So if there are no other questions, we can end here. Thank you, everyone, and we'll make a post and post the slides in the notebook on the course webpage.